Hey everyone, welcome back to Code in Motion. Today we're looking at LeetCode problem number 3, longest substring without repeating characters. So we're given a string s and we need to find the length of the longest substring without repeating characters. Let's take a look at an example over here. And first, let's just define what a substring is. A substring is a continuous subset of a string. So ABC is a substring, BB is a substring, the letter B alone over here is a substring, A is a substring, it just has to be continuous. So any continuous subset of the string. What you cannot do is take one letter here, like a B, then skip the C, and then take an A. So you cannot skip any letters in between. Now in this case, the longest substring we can take of S without repeating characters is 3. You can take ABC over here, you can take BCA over there, you can take CAB over here. It doesn't matter. They just want to know the maximum length, which is 3 in any of those cases. So first I just want to discuss the brute force solution that is going to use a double for loop and 2 pointers, I and j, and we're going to move j as far as we can until we detect a duplicate element. Now, what data structure are we going to use in order to detect duplicate elements? We're going to use a hash map, and that hash map is on the right-hand side called scene. Now, the reason we use a hash map is because a hash map has constant time search. At every single iteration, we could ask ourselves if we've seen that letter before by checking the hash map in constant time. And so you see in this case, we found a C, and since C is in the hash map, we know we saw it before. So it gives us the opportunity to reset the algorithm. So over here, we scan Z, then we scan C, and for every element we scan, we add it to the hash set. And if we've seen that element before in the hash set, then we break out of the loop. Now, every time we break out of the loop, we update the max length, the global max length, which is at the top over there in blue, just to keep track of the maximum length throughout the algorithm. Every time we reset I and j, we reset the scene hash set as well, just to reset the elements that we're keeping track of. Okay, and now we're going to go to the last element, which is just B in this case. And we're done. Now the length of the longest substring is 4. And what's the time complexity of this? The time complexity is O of n squared because we have a double for loop, and we're using O of n space for the hash set. Now, the question we want to ask ourselves is, can we beat this? Can we beat O of n squared? Can we only iterate through the array once instead of using a double for loop? So it turns out we can beat O of n squared by using a common pattern and technique called the sliding window. For the sliding window, you use 2 pointers. Even though we're not going to use the double for loop in the code, we're just going to iterate through the array once with using 2 pointers and being smart about how we increment those pointers. And so we're still going to have an I and j pointer, but in the sliding window technique, the idea is you move your j pointer as far to the right as possible until your constraint is no longer true, and then you move your I pointer closer and closer to the j pointer to make your constraint valid again. In this case, in our problem, the constraint is that our substring, or the characters within our sliding window, need to be unique. And we're going to see how that looks shortly. The only other difference is instead of a hash set, we're going to use a hash map because it's going to be useful to know the index associated with every character. And we're going to see why as well. So let's start this algorithm by moving j as far as we can. So j starts out at index 0 at a, and we're going to ask ourselves, have we seen a before, right? This is kind of the same concept to the brute force solution. Have we seen a before? We haven't in this case. The hash map is empty. So let's add a to the hash map. And we're gonna note the index. The index we saw a was at 0. Okay? And now we're going to update the max length. It was 0, now it's 1, so we update it to 1. Now we move j along, right? The idea is we're going to move j as far as we can, and then if we find a duplicate element, then we're going to have to move I, but we're going to deal with that when we find a duplicate element. For now, move j as far as we can. So now j is at b. B is not on the hash map, so we haven't seen it before, so we could take it. So let's take b and add it to the hash map at index 1, and let's update the max length to 2. Right? The substring AB. Now move along j to c. Is c in the hash map? No, it's not. So add it to the hash map. And let's update the max length to 3, ABC. Now move j along to a. Now this is where it gets interesting, right? Is a in the hash map? It actually is. And I have seen a before at index 0. And so right now, what do we need to do? We need to update the I pointer, right? The I pointer has to move. But where do we move the I pointer to satisfy the constraint of only having distinct elements or distinct characters in our sliding window between I and j? Well, that's why it was useful to use a hash map in this case, because we have the index of a. The index is 0, right? And so all we need to do is move the I pointer one past the last time we saw a. In this case, move it to index 1. Since the index at a is 0, just 0 plus 1, and now we satisfied the constraint again. We have distinct elements or distinct characters in our sliding window. And so now we can update a in the hash map. It's no longer index 0. The last time we saw a now is at index 3. Let's update our max length. In this case, BCA is length 3, so the max length doesn't change. Now we move along j to z. Have we seen a z before? No, we haven't. So let's add z to the hash map. And let's update our maximum length. Now it's 4. Okay, let's move along to c. Have we seen a c before? Yes, we have, right? We have seen a c at index 2. And so once again, we need to move the I pointer. Where do we move the I pointer? Well, one element past the last time we saw c, right? And now we're valid again. We have distinct characters. So let's update c in the hash map. The last time we saw c now was at index 5. And let's update our max length, but in this case it's 3. 4 is greater than 3, so we have no change. Now we go to b. Have I seen a b before? Yes, I have, right? I have seen a b before at index 1. So I need to update the I pointer, right? Well, do I? Do I actually need to update I in this case? We don't, because the last time we saw b was actually before this current substring, right? We're only interested in the substring between I and j, inside of the sliding window. The last time we saw b, it wasn't contained in this substring, right? And so there's no reason to move I. We're still a valid substring. And so you'll see how this looks in the coding implementation, but if we need to move I to a previous element that's less than I, we actually don't move it. We keep I at the current position. And so in this case, we're just going to update the value of b in the hash map to the current index, and then we're going to update the max length. In this case, it stays 4. Now let's move j along to the next element. In this case, it's b. Have I seen b? Yes, I have. And in this case, b is within my sliding window. So I have to update the I pointer to be one past the last time we saw b, and we're going to move I to j. Now we update b in the hash map to 7, and we update the max length. In this case, it remains 4. And we're done the algorithm, right? The length of the longest substring is 4. It's either BCAZ or AZCB. It doesn't matter because we just care about the length. And what's the time complexity of this algorithm? It's actually O of n, right? Even though we had 2 pointers, we didn't use a double for loop. We were very smart about how we incremented the pointers. And so in the worst case, we're just going to visit every element twice, but that's still O of n. It's not O of n squared. And the space complexity is still O of n because we have a hash map. All right, so let's code out the solution. First, I'm going to initialize my variables. So I have a scene hash map, and this is going to be the character to index, right? Just so we remember. I also need to initialize my I pointer, and I also need to initialize my result. In this case, the maximum length will just be initialized to 0. Now I'm going to start the sliding window technique. So for j in range len s, we're going to move j as far as we can, right? So the current character is equal to s at j. And if current character is in my hash map, so if I've seen it before, then we need to move the I pointer, right? So we need to say I is equal to seen at the current character plus 1. We need to move I to the last time we saw this character plus 1. However, remember the edge case where the last time we saw this character, it wasn't a part of the substring, right? So we shouldn't move I. In this case, what we're going to do here is say I is equal to the maximum between I and seen current character plus 1. This will ensure that we never set I to a lower value than the current value of I, right? So it's just a neat trick over here. And then we're going to say seen of the current character. So we need to update the hash map, right, with the new index of the current character. So this is going to be J. And then we need to keep track of our result, right? What is the maximum length of the substrings that we're scanning? So res is equal to max res. We always need to make sure that we check the current maximum result that we have so that we don't change it to a lower length. And the current length at each iteration is just j minus I plus 1. Okay? And that's the entire algorithm. We just return back the result at the end. And let's run this to verify that it succeeds. And there we have it. Thank you so much for watching. If you're interested in more content like this in the Blind 75, be sure to subscribe and like the video down below. It means a lot. I'll see you in the next one.